Page 579.
Everyone who died.
Another way to look at kinetics and rates of reaction is through something that is called collision theory. It should make sense to you that if I have A plus B reacting to form AB, that in order for that to occur, they have to collide. Okay? That ought to be obvious. But they don't just collide. It's more than that. Okay? There's two conditions that apply. They have to collide with enough energy, enough of what we call activation energy in order for that reaction to occur. And they also have to, some reactions, they have to have proper orientation. So if these two things, if this is A and this is B, and they're going to come together, and they have to come together like this, they have to be oriented like that, then if they hit like this, that's not going to work. If they hit like that, it's not going to work. They have to collide with a certain orientation. That obviously would be truer for larger molecules than it would for very simple molecules. But some of those things, their orientation really matters. When I was in petroleum engineering a long time ago, one of the things that we used to have to do is we would have to calculate the volume, let's suppose, of the oil that we were going to produce. Now this oil is 7,000 feet below the earth, and it's sitting in rock. And so what you did was you calculated the volume of the rock. And these are these huge formations that contain the oil. And if I was to take some sand and put it into a beaker and really pack it down, and then start pouring water in there, would the water stay on top of the sand, or would it go and soak into the sand? Obviously, it would go and soak into it. Y'all have done that before. You've also been, like, if you've been to the beach, then you have seen wave come up, and you can see the sand, and it looks like it's dry, and it gets wet, and all that water runs through it. So there are pore spaces that are in the rock. And the amount of pore spaces that they have, that's called the porosity of the rock. These void spaces that are in the rock. The highest you can get just between the rock particles is probably 6, 7, 8%. There are places, well, I don't want to go into that. So it should be obvious that if this oil and gas is, let's just say that this is oil, we have oil and water that is sitting in this rock in these pore spaces, then if I'm going to calculate the volume of the oil, what am I going to do? The volume of the oil here is going to be equal to what? Obviously the volume of the rock, okay, times what?
Porosity.
Times the porosity, okay, and that's going to be expressed as a decimal. So if I had 6% porosity, then I'm going to multiply that by 0.06. And that's all that is it's just talking about the dadgum void spaces that are in the rock. Now, I also have to understand that if the fluid is in there, then I have to understand how much of the fluid is water and how much of the fluid is oil. Okay? So if I have 25% oil saturation, then I would also take this value and do what? I'm real close to just having you guys say, shoot, read the book and learn this stuff. If you don't participate, if you're not going to talk me through this stuff and act like you're involved, then you might as well just do it on your own. So let's get a little bit of participation going. Okay? If the dadgum fluid that I have here is 25% oil saturation and 75% water, If I'm calculating the dadgum volume of the oil, what would I have to multiply this whole thing by?
0.25.
0.25. And by doing that whole thing, I can get the volume of the oil. And it's a difficult thing to do mainly because of that. You don't have these formations that are just these nice cylindrical formations or square or whatever. They have all these funky shapes into them, and so to get a real good calculation on the volume is a very difficult thing to do. Okay? But anyway, this was a way that we could go about calculating what the volume of the oil was, because in the long run, what your goal was to drill down and recover that oil and sell it to people. That's how oil and gas companies make their money. If we're thinking about this in terms of collisions, then we know that we have two factors that are there as well. All right? It should be obvious to you that the rate of a chemical reaction is proportional to collisions. And that if I get 3 times as many collisions, then the rate of that reaction is going to occur 3 times as fast. The more collisions I can get, the faster that whole deal is going to occur. And we spent a lot of time looking at the rate of a chemical reaction. Finding the rate of that, or looking at different rate laws, the integrated rate law, differential rate law. But now we're trying to say, how is that proportional to the collisions that we actually have? The more collisions we get, the faster the rate. And I used to even at a very elementary level, first couple years of teaching, we taught a course that was called physical science, and it was very basic chemistry stuff and very basic physics stuff. And you always told people that how can you speed up a chemical reaction? How can you go about doing that? And the answers to those things were increase the concentration. All right, and we talked about that. I think one day we were in here, and I said if I took a single blue ball and I threw it up into that corner of that room and it started bouncing all around. We didn't have any chairs in here. There was no gravity. And I took a single red one and I threw it into that corner. What are the chances of those two things coming in contact with each other? Very slim. But if we take 150 and throw them into that corner and 150 and throw them into that corner, we're going to get some collisions. And obviously, as we increase the concentration, the more stuff that we have, the more collisions we're actually going to get. We used to do this lab in which you would take a piece of magnesium ribbon and you would put it into some 16 molar hydrochloric acid, and you'd put it into like some 3 molar hydrochloric acid and some 1 molar hydrochloric acid and like some 0.01 molar hydrochloric acid. So you have this little beaker or whatever, and you put that piece of ribbon into that concentrated hydrochloric acid, it was gone immediately. It was just, it's gone. But this, and you had to calculate the time, how much time it took for these things to occur. This one, you put it in at the beginning of the period, it would still be fizzing at the end of the period. Wouldn't even be close to totally reacting. And so concentration, as far as how fast a reaction occurs, concentration is an important thing because you have to have collisions. And if there aren't a whole lot of particles there in the first place, you're not going to get a whole lot of collisions. Now, the second thing, temperature, that we talk about, I like this graph that they have on page 579. When you take a look at this graph, we need to understand something as far as activation energy is concerned. So we said that in order to have what we would call a successful collision, we have to have what? Proper orientation, and we also have to have
enough activation
energy. And the whole activation energy thing is so obvious. I mean, if I was to take some gasoline right now and pour it on the floor and just step back, is that stuff going to spontaneously combust? No. Obviously not. But aren't oxygen molecules hitting that gasoline? Don't we have those collisions taking place? And we do. The problem is that we just don't have enough activation energy in order for that reaction to take place. So when we had these reaction diagrams, what did we plot? You know, when we looked at reaction diagrams themselves, what are we plotting? What versus what? What are my axes there?
Temperature and time.
This obviously is energy. And you know that because you know how much energy you have. You know, this is the energy of the reactants. This is the energy of your products. And then this is either a reaction progress. In other words, it is time. So we have time that's going on down here. And as this reaction occurs, we have this whole situation. Well, if this much energy right there is needed in order for a reaction to occur, all right, what is temperature? Temperature is a measurement of what? When we were doing gases, we had a whole different deal with temperature. We said temperature is average kinetic energy. It's an energy thing. And so we did this gizmo in which we showed a situation in which, like when you have temperature, if you plot temperature, this would be percent of the molecules. This is the kinetic energy itself, and that this is the way that these molecules do. You've got some molecules on this side, you've got some molecules on this side, and this was your average kinetic energy. Is that a knock there? Okay. Am I hearing things? So anyway, if this is energy, if I take that thing and I put it on its side, right now, if this is the average temperature, then what we are showing, if I go straight across, is that that is the only percentage of molecules that have enough kinetic energy for this reaction to take place in the first place. And so as you heat something up, what happens to these temperature curves? You know, I did a little gizmo on this. What happens to these temperature curves as we heat things up? Higher temperature, what would change about this curve? It would shift to the right and it would flatten out. Okay? And so if that same thing happens over here, as I increase the temperature, if this thing shifts to the right and flattens out, okay, now I have all of these molecules that have enough activation energy in order to react. And so it's going to react at a much higher rate because more molecules of the molecules that are making collisions, instead of only a few of those actually being able to react, I have a higher percentage of those things that are able to react. And they show that on the graph on page 579. And what does that E sub A stand for? Obviously, activation energy. You can also make reactions occur faster if you stir them up or if you shake them, and if you have a change in the surface area. Crushing stuff up, powdered zinc is going to react a heck of a lot faster than this big old chunk of zinc would. Okay, because once again, you're getting more collisions because there's more there to collide. Excuse me for being gross. So let's take a look at what they are saying on page 579. All right, this is an important thing. We're starting with the sentence right at the top of the deal. There's a one sentence paragraph. It looks like it says number or whatever. We're starting with the sentence above that. Arrhenius postulated that the number of collisions having energy greater than or equal to the activation energy is given by the expression. And then he has number of collisions, and he says that that is equal to what?
Total number of collisions.
Total number of collisions, which I think they use Z later on. I don't think they use it right here at that particular time. Times E, and this is the mathematical E. That is not... it doesn't stand for something. This is the mathematical E to the negative E sub A over RT. This whole thing is kind of like when we were talking about that porosity deal or whatever. This is just telling you the percentage of molecules that actually have enough activation energy in order for this thing to react. So if I was to take every dadgum collision that I have, if I knew that I could somehow come up with how many collisions were going to occur, only the ones that have the proper orientation and the proper activation energy, are going to actually react. Just because we have a collision does not mean that it's a successful collision. So this guy is coming up with this equation to show how many successful collisions you actually have, Arrhenius, and he's saying the ones that have the proper activation energy are given by that whole situation there. Where E sub A is activation energy, R is the universal gas constant. And that universal gas constant, when we take a look at that, you know, and you're going PV is equal to nRT, and you're using that gas constant, when that is in atmosphere liters per mole K, that value is 0.0821. Okay? But if I look at this from an energy standpoint, and when I do that, I get joules per K mole. That's not true. Is that true? What's the value of R? What are the units for R? Joules per mole K, probably. Anyway, we'll look at it in a minute. I'll find the unit for it here in a minute. But it's a little bit different. It's not this universal gas constant in this unit. It is the universal gas constant, but it is in an energy unit, joules per mole K, I believe. And it has a value of like 8.3151428694385287287. You buying that, Sarah?
Is it really that number, or did you just come up with that?
Made most of that up. Joules per K mole. Joules per K mole. Joules per K mole. All right, going back to what we were reading. So, what we said was Arrhenius came up with the fact that this is the percentage, if you will, of the molecules that have enough activation energy. Where E sub A is activation energy, R is the universal gas constant, T is Kelvin temperature. Kelvin temperature is important there. Make sure it's in Kelvin. The factor E to the negative E sub A over RT represents the what? Fraction. Why is that important when we talk about fraction? Because it's less than 1. I mean, it has to be less than 1. You know, when we said we had 6% porosity, you can't have more pore space than you have volume of rock in the first place. It has to be something that's less than 1. Of all of these things that are colliding, the ones that collide with the proper amount of activation energy would have to be, you know, a fraction of that whole situation. Look at the next paragraph. We have seen that not all molecular collisions are effective in producing chemical reactions because a minimum energy is required for the reaction to occur. There is, however, another complication. Experiments show that the observed reaction rate is considerably smaller than the rate of collisions that have enough energy to surmount the barrier. So there's something else there, and we've already talked about it. And those are the ones that do not have necessarily the proper orientation. Why not? The answer lies in molecular orientations during collisions. We can illustrate blah 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 blah. Therefore, we conclude. Therefore, we must include a correction factor to allow for collisions with non-productive molecular orientations. And then you get into this highlighted deal, and we don't have to read all of it, but look at what it says. To summarize, 2 requirements must be satisfied for the reactions to collide successfully to rearrange to form the products. 1, the collision must have enough energy. 2, the relative orientation must allow formation of any new bonds necessary, blah, 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 blah. So, they come up with this equation, which is a form of what we would call the Arrhenius equation. And it's down at the bottom of that page, and y'all help me out with that, but I think it says this. K is equal to Z times P e to the negative e sub a over RT, and that's negative. Is that right?
Yes.
All right. So here's what this is saying. These are all of your collisions, period. Those are all, every single one of your dadgum collisions. But then what you're going to do is you're going to multiply that by a percentage of those things that have the proper orientation, and by a percentage of those things that have what? Enough activation energy. Very similar to the way that we were talking about what is the volume of the oil in there. You know, it's based upon these, you have to decrease it by these other amounts. Okay, everybody with me?
Yep.
Now they go on the next page. If you turn the page, they take these two things and put them together. And they put an A there, and so you get K is equal to A times e to the negative e sub a over RT, where this A stands for those molecules that do have at least proper orientation in order for it to have the collisions. So it's taking all of those things into account. All right? And once again, this is the activation energy. This is where it gets tough. This is where we have to understand our math here. And by the way, this K is that same rate constant that we've been looking at for a week. It's that same rate constant that we had when we were talking about rate is equal to K times the concentration, blah, 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 blah. Okay? If you take the negative log of both sides of this equation, when I have 2x is equal to some number, in order to solve, 4,732, these things are multiplied together, and in order to solve for x, I do the opposite, which is divide. The opposite of e to some function, of e to the x, is the natural log. So if I take the natural log of both sides of this equation, what I get is that the natural log of k is equal to negative e sub a over r times 1 over t plus the natural log of a. Because those things are multiplied together, the log of a times the log of b is equal to the log of a plus the log of b. So this is all of that right there. I have the natural log on this side. Okay? You with me? Once again, this, people, is in the form of y is equal to mx plus b. We get another equation that is in the form, that is in the slope line form, whatever they call that particular thing. The equation of a line. Okay? So, here's what we can do. We can start performing experiments and we can say, all right, what we're going to do is we're going to look at the rate of a chemical reaction at different temperatures. We know that these reactions speed up at higher temperatures. We know that occurs. You get more collisions. So that rate constant is going to increase with a change in the temperature. Let's see what that change is. So we pick a temperature, 100 K, whatever. This K not being the same as that K. And we get a value, and then we double it or whatever, and we get a value, and we put it another, and we get a value. And if I was to graph that, then what would I get as far as this is concerned? If I was to take these values of K and make that the natural log of K, take these temperatures and make it 1 over T, then what I'm going to get is, once again, if I plot the natural log of this K versus 1 over T, I'm going to get a straight line with a negative slope, and that negative slope is going to be equal to what? Negative e sub a over r. That's my slope right there. R is a constant. R is a constant value. So if R is a constant value, if I want to calculate my activation energy, then I take that slope of that line and I multiply it, obviously by R, and that cancels and I'm left with the activation energy. And this is the only way that I personally, there's probably a bunch of other ways, I don't know. But this is the only way that I know of that in which you can mathematically come up with the activation energy of a chemical reaction. Okay? It's a difficult thing to do. And it's problem 9 on your packet today. Problem number 9 on your packet. I think it's 9. Is it 9? What does 9 say? Calculate the activation energy, blah, 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 blah.
Yes.
Okay? So look on